We shall we'll continue on. Okay, so you guys have a exam on Friday, midterm exam on Friday. It will cover up through the stuff we covered on last Friday. It will not have today's stuff, but I'm going to continue on in chapter 7. Okay, and today we are talking about confidence intervals. And so with confidence intervals, this is kind of our first step into statistical inference, where we are we shall basically start to make conclusions based on limited data. So this is kind of where we have been leading up to. We covered all of the descriptive statistics and then the theoretic stuff, and so today we will begin. So the idea here is, we have some population too big for us to observe directly. Okay, the population has a proportion p. Okay, so some proportion of the population p, it has whatever trait we're talking about. Okay. Now, because the population's too big to observe, we take a little piece out of it called a sample, and we observe the sample. Okay, so we observe the sample. It has proportion p hat. Okay, and so here's the question. Based on the value of p hat we observe, or based on the sample, we observed, and its proportion p hat, can we make any conclusions or statements about the population proportion p? Let me just save this. Okay, so this is what we have, and so we want to. So let me just kind of make an example here. All right, so imagine I've got a big bucket or big tub of M&Ms. This time I did not count all of the M&Ms obsessively. All right, and I'm going to mix it up. I'm going to take a scoop of M&Ms out. Okay, so a scoop of random M&Ms. All right, so I have a total of 200 pieces of candy in my scoop. And we will say 36 are blue. Okay, so that means my sample proportion p hat is 0.18. Okay, my sample proportion is 0.18. Can I say anything about the contents of blue candies in the giant tub? That's what I want to know. What can I say about the proportion of blue candies in the big tub? Okay. What do you guys think? So, you know, I just have 200 candies, which is not very much. It's just probably like a little handful, okay? And those 200 candies, 18% of them were blue, okay? It's coming from a big tub, okay? We've stirred up the tub before I got it, but does this tell me that the tub has a certain proportion of blue? Is the tub 18% blue, or is the tub 20% blue? What's in the tub? Can we really say anything? Maybe, maybe not? Okay. Well, this is the idea behind a confidence interval. We want to say, what can we say about the proportion of blue candies that are in the tub? Okay, so keep that in mind, and I will try to illustrate what we're doing with a confidence interval with I don't know, a little analogous story here. Okay, not even a story. Example, illustration, object lesson. All right, let's. Here's okay. So imagine somebody. Okay, this is a beautiful picture of, what is it a picture of? It's a dog, okay. All right, and the dog is at the 30-yard line. Okay, and so it's on Instagram. You can like the picture. Okay, so we'll say dog at the 30. Where is the owner? I don't know why I'm making hashtags. He is invisible. Invisible leash too. Okay. I'm having too much fun here. All right. Okay, so basically we see a dog on a football field, 30-yard line. But the question is, where's the owner? The owner's invisible. The owner's got an invisible leash, okay? Oh, maybe it's helpful to know that the leash is elastic, okay? Okay. And we want to know, well, where's the owner here, okay? So, well, we know a few things about the behavior of the dog, okay? So we know a few things about this dog, about the dog's behavior. Basically, the dog doesn't like to pull too hard against the leash because that chokes him. Okay. So about 68% of the time, the dog remains within 1 yard of the owner. Okay, and then about 95% of the time, and you guys probably know where I'm going with this, the dog remains within 2 yards of the owner. Okay, and then basically, and about 99.7% of the time, 3 yards of the owner. Okay. So based on this, can we say something about the location of the owner? Maybe. Like, can we guarantee that the owner is between 27 and 33? No, we can't guarantee it, right? Because like it's very likely that the owner is between 27 and 33, but it is possible, but it's 99.7% of the time. So it is possible that the dog and the owner are more than 3 yards apart. Okay, it is possible. It's not likely, but it is possible. So we can't really make any guarantees about the location of the owner. But we can say something like this, okay? So we can say, I am 95% confident that the owner is located between 28 and 32. Does that feel comfortable? Okay, so we can't guarantee that the owner is between 28 and 32, but because we know about the behavior of the dog, we can be pretty confident that the owner is between 28 and 32. But could the owner be at 33 or 34? Sure. Could the owner be at 27 or 26? Yeah, that's also possible. But based on our understanding, we would be surprised if that happened, okay? Could the owner be at, 26? Yes. Okay, but this would be surprising. Surprising to us because that means this picture was taken at one of those unusual times where the dog strayed more than 3 yards away from the owner. Okay, but because we know the behavior of the dog, when we see the dog at the 30, we can be confident that the owner, we can be, fairly confident, like 95% confident that the owner is between 28 and 32. Okay. Is that good? All right. So the reason for this, the idea here is that basically the location of the owner is analogous to the population proportion P. Okay, in that it is unknown to us. Okay. Location of the dog is like our sample proportion p hat. This is known to us. Okay. And the behavior of the dog and leash this is essentially the central limit theorem which states that the behavior of p hat follows a normal distribution centered around p. Of p hat follows a normal distribution with a mean of p, meaning that most of the time p hat is close to p, okay? And so this is why we bothered with all of this theoretic stuff and this sampling distribution stuff, is so that we can come to this point and say, based on the theory, we know that the behavior of p hat is like this, and because we know the behavior of p hat is like this, we can start making conclusions, okay? So now what we can say is, you know, with a sample, if we say, you know, so our sample has proportion p hat, okay, we can say basically something along the lines of, I am 95% confident that p, the location, the population proportion p okay, is going to be close to p hat. So I'm 95% confident that the population proportion p is between basically p hat minus 2 standard deviations, or technically I'm going to just say 1.96 standard deviations, and p hat plus 1.96 standard deviations. Okay? Because the central limit theorem basically said that p hat follows a normal distribution centered at p, and so if we see p hat at some location, we can be pretty confident that p is close by. Okay? In the same way, you know, if we see the dog located here, we can be confident that his invisible owner is close by. Is this okay? All right. And what was the standard deviation when we're talking about sampling distributions? You guys remember? P times 1 minus p over n. Okay. There's a slight problem here, okay, in that we don't know what p is. Okay. We don't know p. Okay. So what we're going to do is we're going to plug in our best guess for p. What's our best guess for p right now based on our data? P hat. Okay, so we're going to plug in p hat instead. And then you might ask, well, doesn't that throw things off? And the answer is yes and no. Okay, so I'm not going to try to prove it to you, but mathematicians have worked on this, and it turns out that substituting in p hat for p in the long run does not create any problems. Okay, so this is an okay substitution. In other cases, like when you substitute one thing for another, you've got to compensate for it later, and that'll come up later on in our course. But right here, it's okay, and we just continue on with life. And I'm going to just say, trust me, it works. All right. Again, if you're curious as to like how does it work, you can choose to major in statistics. I won't stop you, and you can take Stats 100B. It's your mathematical statistics class, and you'll get to do all of these proofs. Stats is a great major, guys. Yeah, and you might have a class with me again, so all the better, right? Maybe. Okay. All right. So so basically, at the putting all of this together, we can say, you know, we observe a sample okay. It has n observations. X quote-unquote successes, and you know, p hat equal to x over n sample proportion. And based on the sample, and our understanding of the central limit theorem, let me just write CLT. We say, okay, and what we say is I am 95% confident that the population proportion P is between P hat minus 1.96 times the square root of P hat 1 minus P hat over n and P hat plus, and we're going to just go out 1.96. So, you know, on some number line, maybe you locate that p hat is right here. Okay, and then you would go basically 1.96 standard deviations this way. And you go out 1.96 standard deviations in the other way. And then you're basically saying, you know, we are 95% confident that P is in this region. Okay. Okay, and I would set up a clicker question here, but I forgot the clicker box in my office, so I can't ask you clicker questions, all right? We'll just pretend like there's a clicker question, and don't just like leave, because now you know there's no questions here. And make me sad. Okay, so but let's try this out. Okay, so we'll go back to the M&M situation here. So we've got M&Ms in the tub. Okay, so we drew a sample of M&Ms out of here. Okay, and our sample has n equal to 200, x equal to 36. So we have p hat equal to 0.18. Okay, and I'm going to say make a 95% confidence interval for the proportion of blue M&Ms in the tub. Okay, and your options are okay, so we'll say 0.17, we'll say 0.170 to 0.190, 0.162 to 0.9. Okay, go ahead and try this out. So we're pretending this is a clicker question despite no clicking. I'll color in my M&Ms. If you closed your eyes, do you think you could tell the difference between M&Ms? Probably not, huh? You know, with sometimes with Skittles, it's hard to tell, and they're like different flavors. It's like, well, especially, well, now that they replaced green with apple, it's like it's not as good. But when it was green was like lime and red was cherry, it was hard to tell them apart. Okay, I'm just talking to myself over here. Okay, do you guys are you guys still working? You got an answer? Not yet. Need another few seconds here. Okay, what'd you guys get for your answer? D? Okay, that's the one I got, I think. All right, so you know, we have p hat plus or minus. We can combine both sides into plus or minus. Oops. Z star times what is this? P hat times 1 minus p hat over n. So I have 0.18 plus or minus 1.96 times the square root of 0.18 times 1 minus 0.18 over 200. And I think if I type all of this in, I do 1.96 times the square root, and you type in 0.18 times parentheses 1 minus 0.18 divided by 200, and then close off the parentheses inside the square root, and I have plus or minus 0.053. So 0.18 minus 0.053 is 0.127, and then 0.18 plus 0.053 is 0.233. Okay, and I would say something like, I am 95% confident that the proportion of blue M&Ms in the tub is between 0.127 and 0.233. Okay, is that good? Yes, question. Where am I getting 1.96 from? This is a good question. So this is coming from the normal distribution. So let me, I just want to make sure everyone's got this slide okay, and then I'll flip on and I'll explain this. Okay, so we are getting 1.96 from the normal distribution. So the central limit theorem basically says that p hat, the distribution of p hat, is going to can be approximated by the normal distribution. Okay, and so when we look at the normal distribution, if I want to get the middle 95% here, okay, I would want 0.025 in this side and 0.025 on this side, okay? And if I look up what z-scores correspond to 0.025 and on this side and that side, I would get z is equal to negative 1.96 and z is positive 1.96. That's where I'm getting those values. Okay, so if I want to get the middle 95%, I basically want 2.5% on each tail on the outside. Okay, if I want to get 99% in the middle here, okay, how much would I have in each tail on the outside? If I want 99% here, I would want 1/2 of 1%, right? 0.005. Okay, and what value is going to give me 0.005? $2.58. Is that what you guys find? That's what I find. Okay. All right. And so, and I would have made a clicker question out of this, but if so, on my on the previous slide. Okay. You know, I said I'm 95% confident that the proportion of blue candies in the tub is between 0.127 and 0.233. Okay, I'm 95% confident that in the tub, if I were to count up all the M&Ms and calculate exactly what proportion are blue, I'm 95% confident it's between 0.127 and 0.233. If I want to be more confident that my interval manages to get the true value of p in there, should I make my interval wider or should I make it more narrow? What do you guys think? Wider or more narrow? We would want to make it wider, right? If we want to if we want to make sure we capture the true value of p, we want to cast a larger net, and we would make a wider interval, right? So if we want to be more confident that our interval managed to capture the true proportion p we would make our interval wider. I hope that makes sense. And that's why our z's would change from 1.96 to 2.58. If we want to be 99% confident, we would increase our z, the value we use, from 1.96 to 2.58. Okay? And so kind of the general form of our confidence interval would be, you know, we are blank percent confident that p, the population proportion, is within p hat plus or minus z times the square root of p hat times 1 minus p hat over n, okay? And z star is one, here actually, if we want to be 95% confident, actually okay, if we want to be 99% confident, we would use z is equal to 2.58, okay? For 95% confidence, we would use z is equal to 1.96. Other common values for z would be 90%, would be z star is 1.645. And for 80%, z star would be 1.28, okay? And we could calculate basically any z that we need to use using kind of that same picture. If you want to get like a 96% confidence interval, you'd find 96% in the middle, 2% on each tail, and you'd find the corresponding z, okay? But I don't know, probably because we have 5 fingers on our hand, you know, we generally don't use, we stick to 95%, 90%, 99%, okay? But you know, you want to make a 93.5% interval, no one's going to stop you. It's just less common, okay? But these ones are probably, you know, these 3 are probably the most common intervals. 80% is on the low side, but you could make it, okay? Is that good? Okay. Let's let me ask you a question here. Okay. So previously, from our M&M problem, we came to the conclusion was, you know, I am 95% confident that the proportion of blue M&Ms in the tub is between, and I think I said 0.127 and 0.233. I think that was the answer there. Okay, so we said that was the conclusion. All right, so here's a question, and this would have been a true/false clicker question, but again, no clickers here. Can I say there is a 95% probability that the proportion, 95% probability or 95% chance that the proportion of blue M&Ms in the tub is between 0.127 and 0.233. Okay, so go ahead and discuss with your neighbor whether you think this statement is true or false. What do you think? No one really cares. No, you guys, I don't know. Any, true? Raise your hand, true? False? Okay, okay. All right, well, thank you to those who participated in that survey. The answer is false. Okay, now why is it false? Okay. All right. I was going to do an illustration with a coin, but I don't have a quarter or a coin. Okay, so pretend I've got a coin here. Okay, I'm gonna flip it. All right, and I'm gonna ask you, what is the probability that this invisible coin is gonna land heads? Okay, what's the probability that the coin's gonna land heads? Okay, and you tell me 0.5, right? Okay. So far, we're good. Okay, okay. Okay, it's landed. All right. What is the probability that the coin landed heads? Okay, okay. All right. So you guys maybe still say 0.5. All right. Now I'm looking at the coin that has landed. Okay, and I've covered it up. All right. And I'm going to ask you again. What is the probability that the coin landed heads? Okay, so maybe you guys are weirded out by this. At this point, okay, the truth is those last two questions, what's the probability that the coin landed heads? Those were nonsense questions. Before I flipped the coin, it was valid to say, what is the probability that it will land heads? It was an event that has not yet happened. There was uncertainty about the outcome, okay? Once it landed, there's no more uncertainty about the event. It either landed heads or it landed tails, okay? So it no longer makes sense to ask about the probability of whether the coin has landed heads or tails. Something has happened. You don't know what it is, okay? But there's no longer probabilities associated with it, okay? So at that point, all you can say is, I am 50% confident that it landed heads, or I am 50% confident that it landed tails, but you cannot say there's a 50% probability that it landed heads or tails, okay? Because there's no uncertainty associated with it, okay? When we're talking about the proportion of blue M&Ms in the tub, okay, once we have this bucket of M&Ms, okay, the proportion P is some fixed value, okay? It is not known to us. It is unknown, but there is no uncertainty about it, okay? No uncertainty associated with P. Because P is just the result of counting up all the pieces of M&Ms in here and counting how many are blue, okay? It's going to be some number. We don't know what it is, but it's some fixed value. So it does not make sense to talk about the probability associated with P. It is either going to be in this interval, 0.127 to 0.233, or it's not, okay? And it doesn't make sense to talk about probability there. Okay, so it does not make sense to talk about probability of p, because it's a fixed value, there's no uncertainty. All right, so it's either in the interval or it's not, so we can only talk about our confidence that p is in the interval, but we cannot talk about the probability of p being in the interval. Okay, we'll end here for today. We'll wrap up on Wednesday. We'll see you guys.